We're going to go over exponential and logarithmic equations. Again, this is a pretty hectic one. There's a lot of information. Again, a lot of this you saw in Algebra 2. Probably would have taken you a couple days. We're going to do it in one. So please pay attention and make sure that you attempt the homework, because this is going to be a tough one. So we got example 1. Obviously, these are exponential equations, and we're going to be using like bases to be able to solve this problem. So what do I mean with that? I want that base and I want that base to look exactly the same by using exponents. So in essence, what we're going to be doing is we're going to be rewriting the equation, or we're going to be rewriting the number. So for instance, I can rewrite 125 as 5 to the power of 3. 5 times 5 times 5 is 125. So I haven't changed the number, I haven't changed the value, I just changed the way it looked. And on the other side, it's just the same thing. I haven't changed that one at all. So now notice that the bases are completely the same, and if the bases are the same, we can use a property, this is kind of like a rule or a theorem, I don't remember, but once the bases are the same, we're able to drop the bases. So I'm gonna ignore the bases, and I'm gonna set the exponents equal to each other. So that's gonna be 3x minus 6 equals 3. Again, we are allowed to do this as long as the bases are the same. And now we can simply just solve the equation. So that's gonna be 3x equals 9, and then divided by 3, so x is equal to 3. Same thing for 8 and 4. Wait a minute. I think there's probably a typo here. No, actually no, this actually works. Okay, so same thing. We're gonna try to get the bases to look the same. Obviously, there's no way you could change a to look like a 4, right? Because 4 to the power 1 is 4, 4 to the power 2 is already 16. So there's nothing that could make a turn into a 4. So what we're gonna try to do is we're gonna try to change both of the bases. So 4, I can rewrite it as 2 squared. Okay, and then we still have the x minus 3 on the outside. And then a, I could actually rewrite that as 2 to the power of 3. 2 times 2 times 2 is 8. And I still have that on the outside. Okay, now obviously there's a little bit of simplification that we got to do. We do have a 3, so we're going to distribute that. So we're left with 2 to the power of 3x plus 6. And then we're going to distribute that, which gives us 2 to the power of 2x minus 6. And now you can see the bases are the same, so we can go ahead and drop them. So drop the bases, and now we can set the exponents equal to each other. And once again, we can just go ahead and solve this. I'm gonna minus the 2 to the other side. So that's x plus 6 equals negative 6. And then I'm gonna minus that 6. So x equals negative 12. Okay, and that's basically it. 2x negative 12. Yep, it all looks good. Cool. Now that's using like bases. So when you're able to use like bases, that's an easier way to do things. Now, what if we're not able to use like bases? Well, let's check this out. First of all, we need to simplify this a little bit. So I'm going to move the 5 to the other side. So now I'm left with 7e to the power of 2x equals 58 plus 5, which is going to be 63. Okay, then we still need to get rid of that 7 because we want to have the basis to only have one single number. So I'm going to get rid of that 7. That becomes a 1. So e to the power of 2x is equal to 63 divided by 7, which is 9. So now we got single terms. Now you're gonna notice right away there's no way that we can rewrite those two bases as the same. I can't write 9 as an e, and vice versa, I can't write e as a 9. So in this case we can use the like bases. So what we're gonna do is we're gonna use logs to solve this. We still want to get x by itself, so we can actually log this. And I would suggest that you use natural logs all the time. So what do I mean with that? I need to find x, and right now it's part of the exponent, and the only way to get solve for an exponent or the only way to get it down is by using logs. Let me explain. If I log, or actually ln, if I ln both sides, now remember you could do it because you have an equation. Whatever you do to one side, you could do to the other. It keeps it balanced. So now I have two logs. I have the natural log of e to the power of 2x equals the natural log of 9. Well, why is this helpful? Well, this is helpful because we could use the power property, which we learned last class, to be able to put that exponent down. So now the exponent becomes a coefficient, and I'm left with 2x times the natural log of e equals ln of 9. And now you can go ahead and get x completely by itself. How do we do this? Well, we need to get x by itself, so I need to get rid of the 2, and I need to get rid of the ln of e. So we're going to divide both sides by 2 and natural log of e. Okay, cool. So obviously that becomes a 1, that becomes a 1, and you're left with x is equal to the natural log of 9 divided by 2 times the natural log of e. Now, I totally missed this earlier, but remember that the natural log of e is just 1, so actually I kind of overcomplicated myself here. So x is just equal to the natural log of 9 divided by 2. I should have gotten rid of that way earlier. I should have gotten rid of that here, but whatever, doesn't really matter. So now we're gonna go ahead and put this into your calculator. So ln of 9 divided by 2, which gives me 1.098. Try to always do 3 decimal places, and that's how you solve it with logs. So let's take another example that doesn't necessarily have an e. So this one right here, kind of the same thing. I'm going to add the 5 to the other side, so I'm going to be left with 7 to the power of x plus 2 equals 410. And once again, you can give it a try. I don't think you can use like bases. And the way for you to kind of figure out how or when I'm able to do that is by maybe making a little table. So for example, 7 to the power of 1 is 7. 7 squared is 49. 7 to the power of 3 is 343. And then 7 to the power of 4 is going to be 2,401. So obviously 410 is somewhere in the middle. So there's no way I can rewrite 410 by using 7. So what we're going to do is we're going to solve this by using logs. So same thing. Once the bases are completely by itself, let's go ahead and natural log both sides. And now that we have natural log, we can go ahead and bring that exponent down. So this is going to be x plus 2. Notice that I'm putting them around parentheses because this is technically one single item. And then we got the natural log of 7 equals the natural log of 410. Now in the other example, here we could have simplified this into 1. In this case, the natural log of 7 can be simplified, so we're kind of stuck with it. All right. Well, let's go ahead and get x completely by itself. So I'm going to divide everything by the natural log of 7. That becomes a 1. And I'm left with x plus 2 equals the natural log of 410 divided by the natural log of 7. and then I'm gonna minus 2 to both sides. So that becomes a 1, and I'm left with x is equal to the natural log of 410 divided by the natural log of 7 minus 2. And don't worry about having a whole, a big expression. You're gonna put everything into the calculator, so it should be fine. So the natural log of 410 divided by the natural log of 7 minus 2, and we get x is equal to 1.091. Okay, so that is how we solve exponential equations. So please remember that these ones are exponential by either using like bases or by using logarithms when the answer is a decimal. Now, on the back, we're going to be solving log equations, and we're going to be using this property. And it's basically like having, so let me give you a counter example. It's basically like having log base b of b to the power of x. Well, this is just 1. This is also just 1. So they basically undo each other. They kind of cancel each other because you have an exponent and a log. So that's what we're going to be using. So let's start with a really easy example. We need to get x by itself. So let's kind of isolate the natural log. So I'm going to divide everything by 4. That becomes a 1. And I'm left with the natural log of 3x equals a divided by 4, which is 2. So now I need to get x by itself. Right now, I can't because I have a natural log. So I need to get rid of the natural log. How do we do that? We're going to do the opposite of a natural log. In this case, the opposite of a natural log would be an exponent of the same base as the natural log. Well, what is the base of a natural log? Well, the base of a natural log is e. So I'm going to raise everything with the base of e. Whatever I do to one side, I do to the other. And what I want you to acknowledge is that this is basically represents an exponent, in case you were wondering what that was. All right, so this becomes a 1, and you're left with 3x equals e to the power of 2, which I have no idea what it is. We're going to leave it to the end so the calculator does it. And now we can get x by itself by dividing by 3. So x is equal to e squared divided by 3, which we're going to put into the calculator. Let's see, e to the power of 2 divided by 3, and we get 2.463. Okay, now what if we get a problem like this one where we have multiple logs? Well, we can actually condense this by using our properties of logs. And if you remember from yesterday, we can use the Pareto rule to condense the logs. So we're gonna make them smaller. So remember, when they're adding, we're using the Pareto property, which means we can put the log into one single log, and everything that is inside will be multiplying, which in this case would be the x times the x minus 3. Okay, now notice that this is a common log, which means the base is 10, even though we don't write it down. All right, so I'm going to simplify this a little bit. So I have log of x squared minus 3x. So all I did was distribute that. And now our log is completely by itself. We can get rid of it. So I'm going to do the opposite of the log, which is an exponent. And we need to raise it using the same base. Remember, what is the base of the common log? Well, the base would be 10. And whatever I do to one side, I do to the other. Well, that's gone. And I'm left with x squared minus 3x equals 10 to the power of 1, which is just 10. And what do we have? We have a quadratic equation. As soon as you see that, that's a quadratic equation. And how do we solve a quadratic equation? We set it equal to 0 and we factor it. So I'm gonna move the 10 to the other side, which leaves me with x squared minus 3x minus 10 equals 0. I'm running out of space. And then if we factor this out, what two numbers multiply to negative 10 and add up to negative 3? In this case, that would be 5 and 2. The 5 is going to be negative and the 2 is going to be positive, which means I have two possible answers. I'm going to write this over here. X equals, well, actually, just going to write it over here. X equals 5 and x equals negative 2. Now, why do I say possible answers? Well, when we're dealing with logs, we could have what we call extraneous solutions, and those are basically solutions that don't make the log true. So we have x equals 5 and x equals negative 2. We need to plug them into the log. So let's see, if I plug in 5 in here, that's the log of 5, plus if I plug in 5 there, that's going to be 5 minus 3, which is 2, so that's the log of 2. If you ever get a negative number inside a log, that is incorrect. That is not possible. Logs cannot have negative numbers inside. So 5 works. But what if I plug in negative 2? Well, if I plug in negative 2, I'm going to have log of negative 2 plus, if I plug in negative 2 there, that's going to be negative 2 minus 3, which is negative 5. So log of negative 5. And you can see right away there's a negative inside the logs, which means this is not possible. So my only answer is going to be x is equal to 5. X equals negative 2 is what we call an extraneous solution. Okay. And finally, the last log. So this one, notice now there's a bunch of logs. Well, first of all, we're still gonna condense things. Here's my advice though. If you do have a negative log like this one, move it to the other side. So I'm gonna add the natural log of x plus 1 to this side. Okay, which means that's 0, and you're left with the natural log of x minus 3 plus the natural log of x plus 1 equals the natural log of 7x minus 23. Now, why did I do that? Because if you leave it as a negative, you're gonna have to use the quotient property, which is not nice, and you're gonna get a really ugly equation. So if it's a plus, we could use the product property to condense the log, which means now my log is gonna look like x minus 3 times x plus 1. Remember, this is the product property. When two logs are adding, you can put them into one if they multiply. Cool. Let's go ahead and simplify the log. We're gonna be using the box method. So this is the natural log of x squared minus 2x minus 3 equals the natural log of 7x minus 23. Cool. And now we can go ahead and get rid of the logs. So I'm gonna caret both sides. I say caret because this kind of looks like a carrot, I guess, or that's how they call it. So once I do that, that's gone, and you're left with x squared minus 2x minus 3 equals 7x minus 23. And once again, you have a quadratic equation. You need to set it equal to 0 and solve for x. So I'm gonna minus 7x here, and I'm gonna add 23 here. That's a 0, and you're left with x squared minus 9x plus 20. So what two numbers multiply to 20 and add up to negative 9? Let's see if this works. So that would be 5 and 4. And they're both gonna be negatives, which means x is equal to 5 and x is equal to 4 are my possible solutions. Okay, now remember, you still gotta go plug them back in, and if one of them gives you a negative, then that's wrong. So let's see, if I plug in 5, I'm gonna have the natural log of 5 minus 3, which is 2, equals the natural log of 7 times 5, which is 35, minus 23. So that's gonna be 12, and then minus 5 plus 1, which is 6. So notice that in this case, nothing inside the log is negative, so 5 works. And you don't have to do all of that work. I mean, you can kind of see if it's gonna work or not. So let's say, for example, I plug in 4. So if I plug in 4 here, that's gonna be 4 minus 1, with 4 minus 3, which is 1. If I plug in 4 there, that's gonna be 7 times 4, which is 28. 28 minus 3, it's still gonna be a positive. And if I plug in 4 there, that's 4 plus 1, which is 5. So you can see that 4 is also gonna work, which means both of those are solutions. We don't have a extraneous solution in this case. All right, so I know this was a pretty lengthy one. Go ahead and get started with the homework. And any questions I will answer when I'm back.